An important aspect of A star search algorithm is that it is optimal when it uses a tree search and uses admissible heuristics. So we have this big result that states that if h of n is admissible, means it doesn't overestimate the path to the cost, which means the heuristic that we picked is good, then A star using tree search is optimal. So this is an important result that have an intuitive meaning to it, but we are going to try to write the rationale behind this result. So let's look closer into this statement. It's an if statement, if condition, if h of n is admissible, let's call it P, then A star using a tree search algorithm is optimal, right? Let's call this Q. So we have an if statement that's if P, then Q, that we could write as P implies Q. All right, to prove this statement, we need to use a direct proof, which means that we are going to start from P, from the statement P, that Hn is admissible, and do some work until we reach the conclusion Q, which is that A star is optimal using tree search. All right, so we're going to adopt this kind of proof, but first of all, let's lay down what we know already about the domain. So first of all, suppose we are doing a tree search then, right? So since we are talking about optimality in tree search, and suppose we have two kinds of nodes, goal nodes. Suppose we have, they don't have to be necessarily on the same level, but suppose we have these two goals. One is optimal. This is the shortest, it means that it's the shortest path to the goal, such as reaching, for example, the city of Calgary, right? And suppose that this one is suboptimal, GS for suboptimal, which means that this is another path to Calgary, but it takes longer to reach there. Great. So let's write what we know about, so suppose G0 is optimal, suppose GS is suboptimal. So we are going to use A star, which means that A star is using the function f. We know that f of n for node n is the function, the cost to n, plus an estimated cost from n to the goal. So it's going to be g of n plus f of n, and this is what A star algorithm uses. Okay, g of n is the cost to reach the node n. So if we have a node n on the way, suppose n is in an expanded node in the fringe, such that n is on the shortest path to G0. Means that we have a path from the root or from the initial node. We're going through n until we reach G0. And suppose that n is on the shortest path to go from the root to G0. Okay, then g of n would represent the cost to reach the node n. That's going to be, the path here would be g of n. This would be g of n, right? And the estimated cost between n and G0 is h of n. So that's going to be, the second part would be this one. Okay, so that's g of n, and that's, that's h of n. That's the estimated cost from n to G0, in which we use the heuristic because we don't know. Okay, great. So we have this information. So we have, what else do we know? We know that we are applying the function f at different nodes to know which for which A star knows what nodes to pick. So for G0, f of G0 would be equal to g of G0. Why? Because we are already at the goal, right? So the estimated cost between the goal and itself is 0. So we're going to write f of G0 is g of G0, since h of G, actually, sorry, this is 0. F of G, h of G0 is 0. 0 O, it's optimal, okay? So we have this first result. For the optimal goal, the function at the optimal goal is the cost at this optimal goal. So if I write it in another color, so it's going to be this cost here, right? Because we know the path. All right, so this is the true cost to reach G0. We do the same thing for suboptimal goal. For the suboptimal goal, so g of s will be equal to g of s because the heuristic at g of s would be also equal to 0. So we have these two elements here. We know also for the A star algorithm, A star will pick the nodes with the shortest function, with the smallest function f. So we know that for actually A star will use the fact that the function at g of s will be bigger than the function at G0. Okay, so this is the first part of the, not the proof yet, but this is the first part of, or the first element that will help us make the proof. So this is from just really what we know about A star and what we know about being in a goal, whether it's optimal or not. Okay, so we are going to start at P and we want to prove Q. P is what? P is h of n is admissible. What does it mean for a function or heuristic h to be admissible? So from the previous slides, we know that this means that h of n is less or equal than h star of n, where h star of n is actually the true cost to the goal. So since h is admissible, so we suppose that the heuristic will never overestimate the cost to the goal. So given this inequality, this inequality here, let's add g of n on both sides of the inequality. So we will have h of n plus g of n is less or equal than h star of n plus g of n. Okay, this left part here is f of n. This is the function at the function at n. And now the right-hand side can be written as g of go, because g of n plus h star of n will simply be the cost to go from the root to the node n, right? And then plus the true cost to go from n to go, which is the optimal goal. So it's going to be f of g0. So from this result, we have that g of n plus h of n, which is f of n, less or equal than f of g0. So we have two important results, which is that f of g suboptimal is bigger than f of g optimal. And we have a function, the function at n, at a node that's actually on the way to reach the goal, is less or equal than f of the function at the optimal goal. All right, so from these two results, right, 1 and 2, we could conclude that actually f of g suboptimal is bigger than f of n, which means that a star will never select a suboptimal goal during the search rather than selecting n. So n will be always selected before gs, which means that the a star will always select the node that will lead it to the optimal goal, and a star is hence optimal. Then from result 1 and result 2, we can conclude that f of the goal, the suboptimal goal, is bigger than f of at a node n that's actually an expanded node on the path to reach on the shortest path to reach go. From this result, it means that whenever a star needs to decide, it applies the function on the nodes. It will always find that the function at the node n that's on the shortest path to go will be always less than the function at a suboptimal goal, which means that a star will never select gs, it will select rather n. Which means that the search is actually optimal, because we always will go toward go rather than to go gs.